Hi everyone, today we are going to learn about the physics of music. So let's start without wasting any time. The first thing we need to understand is what is a wave and how is a wave different from matter. If I take a marker, is this a wave or matter? The answer is it is matter because it occupies a space. So if another marker wants to take the same space, it has to say excuse me and then it can take the space. It can't overlap on top of this marker, right? Waves on the other hand, they can actually overlap and produce beautiful patterns, music, which we will learn in this video class. So let's learn what is a wave first with a demonstration. So you see I put a paper clip here on the fourth string counting from the bottom, and if I pluck this, you can see the paper is getting disturbed, right? So I have created disturbance here, but why this paper clip, that is this side, has got disturbed? Because whatever disturbance you created here, that is moving along the string. This kind of propagation of disturbance is what we call wave propagation. Mind you, in this wave propagation, the particles of the medium themselves are not going forward. Obviously, the particles of this string did not go forward. But what happened was this part got disturbed and slowly the disturbance was transmitted. This is what we call wave propagation. Having learned what are waves, now it's time you learn what are standing waves. In a musical instrument like guitar, you will find the two ends of the strings are fixed, which means if you plug the string at some point, the disturbances which are created, they travel towards the ends and then they are reflected. So you have two waves, one the incoming waves and the one which are reflected waves. And these waves interfere in the same string. Interfere here means they overlap. And when they do overlap, at certain frequencies, they produce wonderful looking patterns. And yesterday, I tried to do this experiment with the help of a rope. I tied one end of the rope to the window and the other end I tried to oscillate. So as I apply different frequencies to the rope, you will see the rope vibrates at different shapes. But why are they called standing waves? Isn't it waves propagate forward? So why are they called standing? Well, if you notice the previous demonstration, then you may have seen that at some point the string did not have much amplitude, did not have much vibration. Those points are what we call notes. And if there is a note, energy will not be transferred from here to there. And to explain that, please see the next demonstration. You can observe when I plug the same string, the paper clip will vibrate, which means energy is getting transferred. But if I create a note by pushing this same string hard, then this point now cannot disturb. So now if I try to create a disturbance by plucking the same string, you see the paper clip is not getting disturbed. In other words, if there are notes present in the medium, then the energy is not getting transferred. It is only oscillating back and forth. And that's the reason why we call standing waves standing, because the energy is not walking forward but just oscillating up and down. So now you have realized that if you have a string which is fixed at two ends, then you can make it vibrate at only certain frequencies. I was not able to make the string vibrate at this frequency because it requires a very fast movement of my hands, and because of the inertia of my hand, I really can't do that. You can do it with electrical oscillators. However, mechanically it is not possible for me, but I did produce these two modes of vibration, the types of vibration. So the first shape in which the string vibrates, if I say it has a frequency F, then this is what we call the first harmonic, which is also called fundamental. And the second one has frequency twice, which is called obviously the second harmonic. And the third one has frequency 3 times the first harmonic, and that is what we call the third harmonic. The frequency corresponding to the first harmonic depends on the properties of the string, like the length of the string, how heavy the string is, in other words, what's the mass of the string, and what tension is there in the string, right? If the string is more tensed, then you believe that it will vibrate more faster, therefore with higher frequency, isn't it? So the relation for this frequency is given by 1 by 2L root over T by mu. So here L represents the length of the string, T represents the tension in the string, and mu represents the mass in the string per length. Per length here means you need to divide by the length of the string. Now what you need to focus here is if you change the length of the string, the frequency also changes. So in other words, if the length increases, the frequency decreases because it is inversely proportional. Whereas if you notice here, if you increase the tension, the frequency will increase, and if you increase the thickness of the wire, why thickness I'm saying, because if you make the wire thicker, then obviously it will have more mass in the same length. So if the wire is thicker, it will have more mass per length, therefore it will have less frequency, right? So let us try to see all this in a demonstration. Please observe this. So as I decrease the length, you can see the pitch, which is the frequency of the sound, has increased. So decreasing the length of the string increases the frequency. Keep this in mind. Also notice that the lower strings are thinner and the upper strings are thicker. So keeping the length same, if I plug the lowermost string, the thinnest string, it creates a much high frequency sound than the thickest wire in the guitar, right? Let's continue with harmonics. I call these harmonics as the atoms or the building blocks of music. Now, why do I say that? That's because just like atoms combine in different form gives you different objects. Similarly, these harmonics, when they combine in different proportions, different amplitude, they give different sound, different music. So the reason why a string of guitar or a string of sitar or a flute, when all of them are playing the same note, why do they sound different? That's because though the note is same, though the fundamental frequency may be same, the constituents, the harmonics which are present in that sound are different, and that is what we call the quality of the sound. Now Pythagoras, the same Pythagoras whose theorem you know, during 600 BC, which means around 2600 years ago, found that if you take two different strings with different length and you plug them, then depending on the ratio of these lengths, the two sounds produced by them will combine and produce a pleasant sound for us or an unpleasant sound. When it is pleasant, we call it consonance, and when it is not pleasant, we call it dissonance. Now what is the condition? The condition is the ratio of the lengths, which also means the ratio of the frequencies, isn't it? Because already I have shown you the frequency is inversely proportional to the length. So when the frequencies or the lengths are in the ratio which are simple ratios like 1:2, 2:3, 3:4, etc., you get a pleasant sound from the two strings when they combine. However, when the ratio is not a simple ratio like these ones, which are called rational numbers, but But when you have irrational numbers like root 2, okay, or pi, then you get a dissonant sound. You don't get a pleasant sound. So as we discussed, let me try to show you. When I play multiple strings such that their frequencies are in simple ratios, they produce a pleasant sound. I have taken as an example the C chord, where I am holding three strings which are called C, E and G, and they produce frequencies in the ratio 4 is to 5 is to 6. Quite simple ratio, right? Let's see the sound. Now, if I keep the shape of my fingers same, but I change the frequency by changing the length, let's see what sound I get. It's not a pleasant sound at all, right? Pythagoras was also one of the first to make a musical scale. If you look at this frequency f and this frequency 2f, the ratio of this would be 1 is to 2. It's a very simple ratio. So when these two are sounded together, they produce a pleasant sound. We call them octaves. But why are they called octaves? That's because octaves usually stands for 8, right? So why are we calling it octaves? That's because between F and 2F, we have 6 more notes. So when you start from here and you go here, you get almost the same sound because they are so pleasant. They are like almost the same. They merge into one another so beautifully. So this one is in our Hindi musical scale. This is what we call the sa. Then we have the re, ka, ma, pa, dha, ni, and this sa is given the same symbol. That's because this one produces such a pleasant sound with this one that they merge so beautifully. So we have given them the same name itself. However, notice that this sa is having higher frequency than this sa, and I would like to show you with a demo. So you remember that if I decrease the length of the string, the frequency increases, right? So I'll start from the small frequency. So this is my sa. So this gives you the second sa, which I hope you clearly heard has higher frequency than the first frequency. Also the notes in the middle, they sounded all very nice. So if you try to find their frequencies and take the ratios, you will get simple ratios. So at the end, I would like to end this video by saying that whatever I explained or taught is a very small part of this huge knowledge that we have in the subject of physics in music. So I hope this video would be the starting step for some of the students. Thank you.